Okay, hi everyone. In the interest of time, and because I can't wait to hear his talk, I'm going to introduce our summer speaker today, Biprateep. So Biprateep Day earned his PhD in physics from the Department of Physics and Astronomy at the University of Pittsburgh in 2024. We were then very fortunate to have him join us in that same year, as he's got a long list of affiliations. Eric and Wendy Schmidt, AI Science Fellow at the Department of Statistical Sciences and the Vector Institute for Artificial Intelligence. He also holds a CITA Fellowship and a Dunlap Fellowship, or at least an appointment, I think.
Job security.
Yes. His work involves developing statistical machine learning tools to study the formation and evolution of the universe and galaxies. He also works on designing large astronomical sky surveys, which enable such statistical studies as, and is a builder of the DES, the DESI, Dark Energy Spectroscopic Instrument collaboration. Today he's going to be telling us about photometric redshifts for next generation sky surveys. Thank you very much. Please take it away.
Thanks, Ray, for the lovely introduction. Glad all of you came. So I'll be talking about some of the things I've been working on over my PhD and over the last 1 year here at UT. All of them related to making maps of our universe. Before I begin, I would like to thank this group of people, primarily from the University of Pittsburgh, Carnegie Mellon, and the University of Toronto. And thanks to these people for paying my salary at different points of time. But a lot of other people will not be mentioned explicitly. They're part of this enormous and amazing group of people, part of the DESI collaboration, and they, even though not explicitly mentioned, have played a big part in whatever I'm going to talk about. So, as I said, I make maps of our universe. The fundamental question is why care about that, right? In the end, you will get this beautiful Google map, but for the universe kind of thing, where we know the three-dimensional location of every possible galaxy in the universe. But it is often the first step for doing any form of extragalactic astronomy, regardless of what your specific science use case is, actually. It may be, if you want to see how galaxies in our universe change over time, since knowing distance can tell us about the absolute quantities of any of these galaxies. It can also be if you just don't care about individual galaxies, but consider universe as a whole as one entity and want to study the bulk properties of the universe, or cosmology, as we call it. Or if you're interested in these transients, which are flashes of light going on the sky. We still need to know where they are to do anything about it. So long story short, it doesn't matter what you're interested in. The first thing all of us care about, as long as you're looking at anything beyond galaxies, is the distance or the redshift of the quantity. So the question is, how do we measure the redshift of the quantity, or we measure of the object? We measure distances with a proxy called redshift. I don't have to explain that part to most of you here. The good old technique people have been using, at least since Hubble, is you take the light from a galaxy, collecting it with some kind of apparatus, you make a rainbow out of it, and when you do that, you will see that light doesn't come in any form. There's certain patterns, emission and absorption lines, and we compare which wavelengths we see it from our observed data with respect to where we should expect it. And we will see that if we stretch, it's not a redshift, it's a red stretch. If we stretch the spectra of an object and find that stretch factor to match what we would see in a laboratory, that shift is called a redshift. Fine, this process is very expensive. We cannot do it at scale, given there are hundreds of billions of galaxies out there. If we need gigantic telescopes, we need a large amount of time, simply because of the fact that when you're taking a spectra we are breaking down the light coming from galaxy into tiny bits of wavelength, and we need to gather enough number of photons per unit in this tiny bits of wavelength to make any kind of measurement. This process inherently is quite expensive. So what do? We try to make a compromise and do these measurements. They are called photometric redshift. It's essentially boiling down to coming up with an estimate for the redshift using photometric data alone, using images alone. Sorry. The reason it works is because images are just a very chunky version of the spectra. And when the spectra gets redshifted, there are tiny changes that happen in the images itself. And this is a dummy picture where we may not be able to see whether it's redshift 0.01 versus 0.01001, that information is lost out, but we can still tell something about the redshift of an object. The information is there. And because of this, we have devoted a lot of new infrastructure in creating these massive data sets which have only images. This include the Rubin Observatory, Nancy Grace Roman Space Telescopes, and Euclid, cumulatively tens of billions of dollars there. And I think York is involved with all of the three, yeah. And they primarily take images. So the thousands of astronomers that will need to do science with any of these gigantic data sets need to rely on photometric redshifts as the first step before they do any science with it. Doesn't matter what the science goal is, again, as I said. So, I hope I have impressed on you that why this is an important problem, especially right now, given where the community is heading. So, what considers a good photometric redshift algorithm? And I will quantify this using two words. The first is called performance. When I say the word performance, it means our ability to predict the redshift of a quantity for one single quantity as close as possible towards the truth. And also quantify the uncertainties, but it is an individual property. How well we can do on one single object. And this is very important. This performance criteria is very important for, like, if you want to study galaxies or mass bulk properties of galaxies, or like clustering properties of galaxies, and also any form of transient cosmology. And for the new experiments to deliver what we promise that we will deliver to the scientific community, this performance as measured with the scatter versus the truth should be like around like 5%, let's say, of the truth. The second thing we also care about is also our ability to find the distribution of redshifts for a given collection of objects. This property we will call characterization. In this, the difference between the previous thing is that now I'm not caring that much about the individual objects, but I really care about figuring the ensemble distribution of galaxies of certain properties, of certain class. We will call it tomographic bins, but we want to find the ensemble distribution, and that requirement I'm calling characterization. I'm not calling, the community calls characterization. And to deliver whatever we promised, the characterization should be within 0.2% of the moments of the distribution, of the true distribution of redshifts. The sad part is, right now, the state of the art is almost 10 times away from the requirements set by, let's say, LSST, Roman, Rubin, doesn't matter. So how do we try to tackle the problem? Okay, the quick side note I forgot. Why do we care about characterization? It's primarily because weak lensing has turned out to be a very important tool in studying cosmology in a way which is fairly independent of the previously known probes. So in this situation, we cannot measure the lensing signal for one object, but we can make good measurements of a bulk of objects, and hence we need to know the redshift distribution for a bulk of objects. And that's why characterization is very important. So how do we figure that photosy out now that we know what it is? So there's two general classes of methods. The first one I would call a model-based methods. It is essentially, we take the photometry, you take the images, you fit a circle around the images, find out the total light coming from them, we call it colors and magnitude, and try to come up with a theoretical model of the spectra that best describes these images. And there's like, yeah, Chris.
So this set of bands
Yeah.
has a venerable history. Why is it still being used? Why not double it or triple it, the number of bands? Why is it optimal?
No, it is not. It is entirely governed by the economics of that experiment. So,
But obviously, 10 or 15 bands is still much cheaper than the spectrum.
True. So people, we try to optimize between numbers and the total number of objects versus the number of bands. The moment you have more bands, you're reducing the number of objects you can get within the probe. So I guess as a community, we do that cost benefit analysis and then figure out the bands. Yeah. So, and there are, like, for example, one of the reasons Roman was launched was to add the number of bands to the Rubin, because the Roman footprint entirely overlaps with Rubin. It's a subset of Rubin. So people are also trying to increase that.
Can I ask something here?
Yeah.
So, like, this is fantastic that we are using theory to match to observations. But I think, as you know from James Webb, for example, we're finding things that have spectra that are completely not explicable by any theoretical model. So do you also have outliers? Like, are these algorithms flagging like this thing is completely an outlier, we've never seen it before? Or will it try to fit it to something that you input?
So that's a great question. So the way things are being, okay, this is, I guess, this part of it.
Exactly.
Yeah, so the pros of these kinds of method is that we can make a measurement given one object, but this entirely is under the assumption that my theory is correct. So I don't think we can flag outliers because in any kind of model-based approach, we put an assumption that our model is correct. So my results might be quite wonky.
Yes. For example, if your errors are super high, does it not flag that this is something I've never seen before, or is
so that's a great question, and that's like the second part of my talk. But long story short, you can have larger errors, but if we are overconfident on our models, any kind of model-based inference will always put higher weight. It's very hard to make it work. So that's why we have the second class of methods, which is entirely data-driven, where we say that we know the redshift for a subset of objects, and we create some kind of very flexible mathematical model. I do not care what that model is, it just connects the inputs to the outputs. Here the inputs are my photometry, the outputs are the redshifts. The pros is that by far they work like way better than template fitting, the model-based methods. The con is they work better when we have enough training data. You cannot do this approach with one galaxy, like the James Webb situation, for example. The other thing is all biases that are present in your training data get imprinted in your results themselves. So here now comes my work. So how are we trying to tackle these different challenges? The first thing is how can we improve performance, but now doing something slightly different. The first thing, traditionally what we do is we take images and then essentially fit a circle or an ellipse around the image and calculate the total amount of light coming within that circle. By doing this process, we are throwing away a lot of extra information that is present in a resolved image. Like common sense would tell you that something far away looks smaller and fainter, like in a surface brightness far away, than something nearby. The question is, why are we not using that? Well, one reason is that until very recently, we didn't have the technology to do that. But now we do have that technology, so why not do that? So we did this experiment, and that technology is called AI. Well, this is the last time I use that word. Let's call it this simple mathematical multiplication function, which is called an artificial neural network. But the simplest unit of computation here is a product of numbers followed by an addition followed by a nonlinear function. So if you have a bunch of numbers, x1, x2, x3, whatever, I take a linear combination of them, here omegas, I add them together, linear transformation, and then I pass it through a nonlinear function. A nonlinear function can be anything, but let's say 10 hyperbolic is one choice, and you get an output. But you don't need to stop there. You can do this operation again and again. This output goes back into another function, which goes back into another function, and potentially you repeat it for billions of times to get what we call a deep neural network. And these quantities are multiplying with, these are unknown quantities which are found by some optimization process, similar to how you would fit a straight line to a model, let's say. The good part is you can show that in some limits, these are universal function approximators. So given an optimization went to the minima, you can create any function in a very compact number of mathematical multiplications. So this is actually the 1950s version of a neural network. People just didn't have GPUs back then to make it work. The success of people at U of T, Hinton et al., is that they figured out the engineering part of it, though the science part of it is at least 70 years old. Anyways, but now people have gone one step further. It's just like, okay, why are we thinking of it as like scalar multiplication, things like that? What if we have my smallest unit of computation as a vector rotation transformation? So I have a vector, multiply with the matrix, I do not know what it is, it rotates the vector, and then I put it through a squashing function, which is a nonlinear function, and I do it over and over again. So I use this word capsules because Hinton 2011 coined this word capsule, and it was trendy when I started doing this word. But these vectors are now called tokens. Capsule networks are called attention mechanism, and a well-engineered version of capsule network is now called transformers, which is essentially powering everything in AI space right now. I'm using different terminology because when I started doing it, it wasn't the name people use, but things change on a day-to-day basis in the machine learning space, so bear with me. But if you're aware of modern terminology, capsule networks are just less engineered version of transformers. So, the fundamental difference between a good old neural network is the way the calculations are done. It's like scalar modification versus vector products. Okay, cool. So now,
so can we just define capsule a little bit more slowly? So each capsule has a different linear combination of the inputs, basically.
Exactly. So you can think of the capsule token. Let's use the word token because that's what people use right now. You can think of it as a column matrix. The next step is you multiply this column matrix with a non-column matrix. Values I do not know. And then after that, the next layer is a non-linear combination of all these vector transformations. And this non-linearity is based on some weights. Those weights are called attention weights, because it's a way of putting attention on which part of the input it is. So yeah, so it's essentially a nonlinear summation.
Also, the capsule is an economical way of making distinctions.
Yeah. Between various parts of the data.
You have a limited number of inputs. Is that the idea?
Yes, and also this weighting part is taking care of which specific parts of the input is important, and I'm not letting the whole information pass through. I don't know if you've seen it's also used in natural language where the meaning of the 10th word depends on a very specific way in the previous words, not equally on the, so it's similar-ish idea, yeah. But it just is a way to do us create, again, this universal functional approximators in a very efficient fashion. So the question is, why do we need efficiency? Because in astronomy, data has always been scarce. So that's why we inherit this architecture. And right now, people have found so much more about this architecture. This is a natural choice for any kind of calculation right now. Back then, we knew less, and we're just going with vibes at them. Anyways, so what we do, we start with the data set, which is images, and then we pass it through this deep neural network. And we, for the sake of efficiency, making the network learn the things that we want to learn, we don't ask it to just predict the redshift. We ask it to solve multiple different quantities, tasks. The reason being, we have seen empirically that sometimes this optimization process does not go to the correct minima. But if you ask it to solve multiple related tasks, you can put it as enforce as a regularization criteria that learn the physically meaningful features that help you to do good in this task. So the dummy task that we chose is classify the shape of the galaxy as a simple disk versus spheroid, and also compress the input image into this 16-dimensional latent space, or a compressed version, and use that to recreate the image again. The idea is that to recreate the image again using the 16 numbers, the 16 numbers should be meaningful enough to contain the whole input data. So what's the result? On the right-hand side, I presented the state of the art from classical machine learning techniques. On the right-hand side is this work. Each data point is identical between the 2 points, 2 plots. The only difference is that the right side plot uses colors, magnitudes, search indices, essentially summary statistics of the image. On the right-hand side, the same data set, but we use the whole image pixels. X-axis, truth, y-axis, my predicted redshift. Now, ideally, if everything went perfectly, everything should fall within this 1-to-1 line. But the next best situation is that I have a very low scatter. And just by eye, you can see, while keeping everything same, just by switching out images, switching out colors and magnitudes with images, you reduce the scatter significantly. And it is almost an order of magnitude difference in various metrics of performance, where sigma is like the scatter, fraction of outliers is the times when I do horribly wrong, and the last one is the bias, that is what is your average prediction error looks like. So one interesting to note is that this end, you will see that this is just because at the low redshift region, we have, any survey will have such a small volume of the universe, you'll have less training data. And this has traditionally been a challenge for any photos algorithm. And we do quite well in this very low redshift regime also. And the same conclusions kind of hold when we look at the performance as a function of redshift, and also a function of colors and magnitudes, as we will see. So the next thing is, by now, I don't have to impress on you that machine learning works. The more pressing question right now is that, why does it work? When does it not work? Because that's something that scientists, or when I use it, the outputs do some scientific analysis, we care about the most. So we did some, it's a work in progress. I'm doing some work on it right now with Josh too, but we did some exploration to see what kind of features are the model learning, and how do they align with our intuition. So this is you can do various checks, but this is the most visual one that I've found. Is, as I said, I am using, the model is constructed to use the 16 numbers, which is a compressed version of the image, to predict both the redshift and reconstruct the image. What if now I take those numbers and just perturb one of those dimensions to see how the reconstructed image changes visually? And we see that those numbers encode things that we generally associate with distance, like the size of the object on the sky, the central bulge to total ratio, things like surface brightness, orientation. And you can do, of course, quantifiable metrics of finding correlations with known quantities, but those are in the paper, you can check out. The other thing is just make a simple, yeah.
So, what are those sigmas?
Or it's like how much I'm perturbing the latent space with the vector with. It's just I'm adding or subtracting as quantity, so I'm using it in units of the standard deviation of the data.
Okay, how does that?
So these are, let's say I have 16 numbers, 1, 2, 3, 4, 16. For dimension 1, I'm adding 1 plus 0.1, right?
Yeah.
So since the absolute numbers do not matter, I'm just taking the standard deviation of all of them. So it's just a unit thing. Choice. Yeah.
So, sorry, please go on.
Go ahead.
Last one. Okay. So here you're changing 4 different properties on the image. So does it so happens that in your 16-dimensional latent space, there are just 4 dimensions that are so well aligned with size, orientation, central bulge, and surface brightness?
Yes. So I cherry picked them. There are other 12 which align with things like colors, magnitudes, but in a talk I'm like, I don't know how to plot them. Just
Right.
So
Right, but for each aligned case, they're just so well aligned?
it turns out, yes.
Oh, okay, that's amazing.
Yeah. I believe this is also because of the regularization. We enforce we really want them to learn physically meaningful quantities. Also with the efficiency. And as you will see, we achieve the same very good performance using a very small amount of training data and computation. Yeah.
So why 16 numbers?
So it is a choice. So we did a grid search. It's the bigger the number, the dimension is, the more computation you spend. But at some point of time, it's diminishing returns. So after checking multiple choices, I saw after 16, it really doesn't matter. Yeah. It's a choice. The other thing is making just a plot of those numbers in 2-dimensional space. I use the dimensional reduction technique to project it into 2 dimensions, because plotting 16 numbers is hard. And you will see that again, these vectors or capsules track a continuous representation of the redshift and also other quantities. This is red means it's a red galaxy, blue means it's a blue galaxy, disk, spheroid, so on and so forth.
So what does the neighborhood mean?
Oh, it is in this region.
Oh,
How many? It's a histogram, pen histogram.
Okay.
How many red disks are there? How many spheroids are there? Yeah. The other thing is, and it's also in our interpretability math, because we are on the journey to understand why it is. Work done by an undergrad I work with, and she recently published, which is amazing, to see now how does this performance, what do we do better compared to traditional methods. One thing we did is check things in groups of galaxy properties. Like you group galaxies by very specific properties, and these are 4 groupings. The first and the second, these are first to third are kind of, let's say, ordered in increasing bulge to total ratio, decreasing bulge to total ratio. And the last one is an interesting case. These are very low redshift galaxies. These look like fuzzy blobs on the sky. Yeah. The one thing to know, interesting we see is that there's a common statistical phenomena in any model. We have known it for a while. It's called attenuation bias. It is when you try to fit any model to a data, the model tends to over-predict at very low values and underpredict at very high values. An alternative word is called regression dilution also. This is one thing we do by switching out images, we do exceptionally better, regardless of what kind of galaxies we're looking at. And there are many reasons for doing it. But yeah, I'll request you to check out other paper to see other interpretability aspects of when do we do better, when do we do worse. But one obvious common sense thing for the very low redshift universe is that for when we have these gigantic good resolved images, some very experienced astronomers can tell you the redshift by eye within 0.01. And these are the kind of intuitions the network is also learning. Like, it's very hard to tell the redshift if it's a tiny dot, but I have seen people predict the redshift by eye by looking at resolved image for the very low redshift universe. So these are work with datasets from SDSS, which has been kind of beaten to death by now, but it's a good test bed. The question is, how do we use these techniques and scale it up to new surveys like Rubin, Roman, legacy surveys, which is also gigantic in area. So that's what we are working on right now, is again, build up on these kind of methods, but also since, as I said, the AI infrastructure engineering part has developed so much, is bringing in a lot of techniques from that. And one of these challenges is people have found that recreating masked data is a very good training strategy for neural network models. That is how language models are also trained, where the model is objective is to predict the next word given the previous word. The generalization for arbitrary data set is you remove a significant portion of the input data and try to reconstruct it, and then use it as a task to train models, and eventually use them to predict redshift. So in addition to the things that I talked about, incorporating such objectives seems to be the way forward and allows us to scale up quite well. So to summarize for now, we have one good way forward to increase the performance for next generation service, and it often is on the order of magnitude by switching out colors and magnitudes with images given enough training data. And we can make these methods reliable, interpretable, without treating them as black box magic tricks, and quite efficiently also. Any other questions? Yeah. No.
Like, how many images do you need, and can you predict, how well you do?
That's a good question. So it depends on, I would say, the redshift range. For, let's say, Rubin-ish things, we'll probably need order of 1 million or so unbiased label data, which is different than what exists already. And I'll talk about that part later.
So that means 1 million spectra.
Yes. Yes.
But you're doing tens, hundreds of millions of galaxies.
Yes. When I said unbiased, is that all data sets we have are not unbiased. So they are color selected, for example.
Right.
It's a good segue to the third part of my talk, actually. Okay. Now the question is, how do we predicted good one single values. For scientific analysis, the other thing we care about is error estimates. How do we know the error estimates are good? And that's also boils down to the characterization of ensemble distributions. These are the two works I did. First one is a more physics paper. The second one is an entirely statistics paper. So choose your poison. But what do I mean by that? What are the challenges? So most Porter's algorithms give you a uncertainty quantification using a probability density function, PDF. That is, it states that how probable a quantity is given a function of redshifts. But it turns out, if you take an off-the-shelf algorithm, these PDFs do not conform to the statistical definition of a probability. What do I mean by that? The first before that is that why do we even care about PDFs as opposed to a good old intervals? It turns out that since photometry is a noisy and kind of redacted version of the spectra, you can end up with a situation where you have two galaxies with very similar photometry, but very different redshift. And there's literally no easy way to quantify that using just one single interval. PDFs, the way to go. Now, once we want a PDF, what do I call a good PDF? It is the definition of probability. If, let's say I have a PDF and I created 50% interval out of it, okay? When I go and do an experiment, the true value should fall within this 50% interval exactly 50% of the time. There's nothing special about 50% though. It should be true for any function of this quantity I'm gonna call coverage quantity. So if I make a plot, diagnostic plot, where I say I have this prediction for this galaxy, some probability, I create a 10% interval, and I go out, do a real world experiment where I collect similarly looking galaxies, measure the redshifts, find how many times the true value falls within that interval, it should be 10. For 20, 30, 40, 50, 90. And when I make a plot out of it, it should follow this identity line. Okay? And this we call the probability plot, or the PP plot. So I didn't invent it. People have been using this metric for a long time. And the LSST desk collaboration about 5 years ago ran this experiment where they tested all the cutting edge PhotoZ algorithms on a very benchmarked photometric data set to see which one should LSST use. How do they perform? What are the uncertainty quantifications? So these are all the algorithms. And now, given what I've told you, which one is the best performing algorithm? Yeah, trains is working pretty good. Which one else? Yeah, ANNZ2, FlexiBoost. By the way, cool fact about ANNZ2 is that it was published, not Z2, but the first one was published when I was born. It is a neural network based architecture. So Ofer Lahav at UCL was doing cutting edge neural networks before they were cool. Anyways, so the good part is TrainZ seems to be working very well. Amazing. It turns out that TrainZ wasn't even an algorithm, they were just trolling. TrainZ is just a histogram of my training set. So I have a training set for which I know the redshift, create a histogram. And for my test set, for the unseen data, doesn't matter what the galaxy is, I always say that my prediction is gonna be this histogram. It's completely uninformative. But in this metric, this is the one that performs the best. So there's clearly a problem with the metric itself. And also, even in this, given this metric, the others also don't perform pretty. Even in this janky metric, the others don't perform perfectly. So there's many problems. Yeah, pretty good.
So, okay, sorry, I'm just trying to understand how this works. So I think what people are doing, at least with the data sets we have now, is yes, they will get a PDF of the redshift distribution. But then you are correlating this with something physical, you know? So for example, you say, for this redshift, this is the kind of masses I expect.
Mm-hmm.
So you fold in, for example, things like masses or luminosity distributions. I don't know, you may fold in beta slope, whatever.
Yeah.
But you are combining this with physical information and how that should evolve as a function of redshift. Sorry, does that make sense?
Yeah, so those go into your prediction algorithm itself.
Exactly.
So for example, Lafare here, they do it.
Exactly. Also, for example, easy.
Yes,
So
Easy also does that.
Exactly,
Yes.
and that is how you zoom in on whether this is, for example, you were telling us that you can have things that look really similar but could be at different redshifts. So, for example, this is how you would distinguish something that is super high redshift versus something that is really low redshift, dusty quest, or whatever.
Yeah.
But is this being folded into these neural networks now, or?
No.
I see.
No. But doesn't matter, even if you don't fold in.
Okay.
Just from an objective point of view, the prediction accuracy, neural networks still do better. It's primarily related just by comparing the truth once you have a redshift measurement, by comparing the truth with the predicted. Given enough data, neural networks still predict better.
So this, I would agree with you on a global basis, but is this also true if you're doing object by object?
That's a great question. That I won't say is it true whether object by object or classes of object based on the amount of training data available. So I would paraphrase the same question in units of training data. So if for a given object class we have enough training data, they do quite well. Yeah. But that also brings in the point of the metrics of how do we know if my predictions are uncertainty predictions are good or not, is these metrics are a bit problematic itself. So even if you did perfectly, since our metrics are flawed, I don't know that I did perfectly. It's a tiny bit of a problem which we need to solve. So the trains example is so blatant that no one will do it in real life. However, you can come up with an infinite amount of situations where you do slightly wrong, but in opposite ways as a function of your input space. And when you look at it as a test ensemble average, you are always doing perfectly. So what we want to progress towards is make this same probability plot, but now one customized plot as a function of my input space. How would I do that? The simplest way would be to just make bins in my input space and make a local probability plot. But making bins always goes out of hand very quickly if you have a very high dimensional space. So it's not a viable way to go. So that's where our work comes in. It's trying to make that viable by creating an estimator for it. So I won't go into the mathematics of it. It's in my extra slide. But what we try to do is we start with some calibration data for which we know the true redshifts, and using which we create a counterpart of this binned probability plot. But now I smoothed over these bins by using a regression method. So I'm using a regression method to kind of predict a smooth version of my localized probability plot, and to create these local diagnostics, which by the local nature, if I haven't said local enough already, cannot be fooled. Now the second thing is, if we have a diagnostic that works well, no one is stopping us from inverting it to say, asking a new question, what should have been a new probability distribution that gives us this ideal result with respect to the diagnostic that I created, right? So it's both ways. I can use the same framework to diagnose existing PDFs, but also if I find something wrong, recalibrate these PDFs to conform to the statistical definition of one. So that's what we did with the exact same data set from what LSST desk used for their controlled testing. So, and to give ourselves the worst case situation, what we did is we start with this blue curve in the top line, which is the histogram of training data set, and try to recalibrate that to get the orange curves. And by eye, again, you will see that the orange curve tracks the true redshift of the object much better than the blue curve. And the second one is also a visual representation of what I did is just plot a histogram of all the redshift from the training set of all galaxies, which look the same by some metric. But yeah, apart from visual metrics aside, you can create quantitative metrics to see that we can use the same data set to do much better in terms of calibration also. And the funny thing is, whatever I said until now has nothing to do with astronomy. I'm trying to solve a regression problem. I have some number of objects, and I try to predict one quantity. So to aid other people to do the same thing, I converted the whole thing in a Python package. And if you know how to use scikit-learn, it has the same API. You declare a model, you do model.fit, model.predict. You can use all of that. And again, I can show plots later on, but people have been using this framework to do things as wild as predicting the intensity of tropical cyclone from a infrared video taken from the space, called having good uncertainty estimates is very important when you want to dedicate governmental resources. So to summarize this part, is photosy distributions better capture uncertainties, and that's the way forward. But traditional methods do not give you a statistically meaningful photosy estimate or uncertainty estimate. But we can create a general purpose technique where we recalibrate existing PDFs to conform to the statistical definitions of it. Now comes to my last part of the talk is I've yapped a lot about using data-driven methods to do all of this. And I started by saying that everything that is biased will imprint on the results. So how do we solve that? Because we don't have the data, unbiased data. So how do we solve this problem? So at this point, even until the future, whenever the Dark Energy Survey DES Year 6 results come out, we are quite convinced that methods are not the bottleneck anymore to use photosys as a tried and tested way to do science, let's say Rubin, Roman, or any photometric surveys. The primary bottleneck is the existence of unbiased data on which our new cutting-edge methods will be trained on. This is a error budget that people from DES did for their new upcoming cosmology results. And you will see that regardless of which kind of bin you're looking at, the redshift sample is the primary, like by redshift sample, I mean the existence of spectroscopic redshift is the primary bottleneck towards delivering science. And people have done this estimate for a long time, like, okay, how much time should it take for us to get a unbiased redshift sample to do science with, let's say, Rubin? So these are some predictions, and I'm just highlighting DESI here because of my bias. And you'll see if you hijack DESI, it will take 1.4 years of continuous observations to get an unbiased training sample that is useful for 10-year Rubin data. This is just outrageous. It's not possible. These estimates were done before DESI existed. These were done by scaling up results from the Keck and other existing cutting-edge telescopes at the point of time. The thing is, DESI exists right now. If you haven't heard about DESI and have been living under a rock, but DESI is this new instrument on top of the male 4-meter telescope, which has this 5,000 robotic arms at its focal plane, each carrying a fiber optic cable, and it can be positioned within some area. It has 3 spectrographs, and it is performing a very wide field survey that is going on right now. I'll show you the statistics. This is the real telescope. That tiny thing is me for scale. But this is where we are at. As of like maybe last month, DESI has collected good spectra of 16 million bright galaxies, 11 million stars, 7 million, 8 million luminous red galaxies, 16 million emission line galaxies, and 4.5 million quasars. Yeah, that's all. But this is quite unprecedented. The first year of DESI data was larger in size than humanity's combined collection of all spectra. Now we are way past that, probably five times of that number.
What's the signal to noise sort of cut?
This is not, I'm not sure because there's no signal to noise cut as such, but it's a second order effect where we say good spectra by our ability to measure a redshift itself. Because our ability to measure a redshift is not necessarily related to the signal to noise of the spectra always.
If you want to use it for other purposes, which some of us might want to.
That is true. That is true. Given the DE in DESI, maybe 50 out of the 1,200 people in the collaboration care about doing anything else apart from target and G. But I would say it is comparable. The byte example is comparable to Sloan. Yeah. And also the LRGs too. The ELGs are not at all comparable to Sloan. And yeah. Okay. So, but having said that, I was pitching it as what we do DESI to use collect spectra that is representative of LSST year 10. Everything that DESI does right now is nothing similar, not at all remotely close to brightness levels of LSST year 10. It is very good at doing something it is designed to do. But what if we use it to do something it's not designed to do? That's what we did. I call it the DESI Deep sample. Well, it's currently the pilot sample. If they give me enough time, I'm doing the full sample. But this is the experiment where we did. So I'm defining an unbiased sample as a sample where we only put the magnitude limit, no color cut, anything else. It goes for now up to the hyperspeed prime cam year 3 limit. It's, let's say, LSST year 3 faintness. We select this galaxies, resample it so that it has uniform distribution in I magnitude because I want to test all kinds of galaxies equally well. And we, in a very simple term, stare at a patch of sky with DESI for however long the instrument gods let us to do it. It's slightly more complicated than that. But we collect that data and process it. And this is what the data looks like. Okay. For people who do not do ground-based spectroscopy on a day-to-day basis, it may not mean much, but this is exceptional. We could not get spectra of something at I magnitude close to 24 by only using the absorption lines until now. Yeah, no one has done this. Emission lines, yes, we have been doing it, but this is insane. The thing that makes it more insane is that you do 5,000 at a time. So it's a very well suited to do these kinds of experiments. Anyway, so we can now test what is the redshift measurement efficiency for DESI for these kinds of samples. And I will point your attention to the center middle plot, where in this time region, you'll see that the DESI's redshift measurement efficiency is matching that of the Keck DMOS telescope. Now, the caveat here is that Keck has an 8 meter mirror. DESI has a 4 meter mirror, which is essentially equivalent to a 3.36 meter mirror because of weird geometry issues. So Keck has 9 times the collecting area as DESI. But if we spend only twice more time, we match that performance while getting 10 times, 20 times more spectra in one go, which is insane. So with this data, we created some predictive models, which I'm not going to go into details, but we collected this pilot data to see can we predict what DESI's redshift measurement efficiency should be for any arbitrary time and magnitude component, and also propagate this whole thing using a Fisher matrix forecasting platform to connect the exposure time to like your dark energy figure of merit kind of situation for making future decisions. Like if I get this, spend this much of time, how much do I do in terms of cosmology? But to summarize this part, if I look at the table again, this 1.4 needs to come down by a factor of 3.5 to 3, which means that it is way more reasonable at this point of time to collect representative training samples that will enable all this data-driven methods I've been talking about. And it's just a matter of investment, and we can do that. Having said that's all, folks. If you have questions, comments, concerns, you can speak of now, or my office is at 1421, right next to the lounge. Feel free to drop by anytime. Thank you.
Very got a lot of questions, but
Well, you mentioned that some of the scientific vibration wants to environment. What are your leading science drivers?
So my leading science drivers is mostly to study galaxies and how dark matter affects the formation of galaxies. But I guess at this point it's all connected. But what I would like to do personally is use these kinds of photometric only samples where you have gigantic numbers of objects to study things like the galaxy halo connection and environments of galaxies. But they have been done before using spectroscopic only samples, but there are many contentious issues.
So what are the implications for transient astronomy if you have this sample of galaxies?
Yes, these are implications are great. You can actually, so two things. You have, with LSST, you have to use photometric redshift to do transient science. There's no other way out. The primary implication is there's no other option. And everything that LSST gonna deliver is primarily gonna be
Is your methodology going to impact what they do?
Yes, especially the ones where we have photometric redshifts with resolved images, because for transient localization, we really do care. It's gonna be relatively low redshifts with LSST, and we really do care about the individual performance.
So the idea here is that you have this ungodly number of transients, and then you can use the PhotoZ redshifts to help focus on which the transients you're going to follow up on spectroscopy.
No, it's gonna be, so that is partially.
You can't follow up on all the
Exactly.
transients
So the way people are going is that ultimately with transients, you'll have the comparison of your distance as measured through your light curve versus distance as measured through the redshift. And there's the relation between them is where all dark energy, dark matter, everything lies. So traditionally on the X1 axis, you have the distance as measured through redshift, is spectroscopic redshift. People have to replace that with photometric redshift.
Well, but of course, you have to also frequently decide what type of transient you're looking at.
Yes.
And there you need the PhotoZ to help refine your judgment.
That's also true.
Or you may need that.
Yeah. Because we don't know whether we saw a type 1a supernova, otherwise how would we figure out the distance from the light curve itself? Okay.
Yeah, this may not be that relevant, but you know what pins are?
Yeah.
So they're physics informed. It seems to me that you want to put as much physics into trying to get these PhotoZs out as you can, namely certain kinds of measurements that you would do on the data that you can say, oh, just go and do everything. But it's probably better, so this is what I'm getting at. There will be different noise levels depending upon the day that spectra have been taken, or photos, the images have been taken. And you have to somehow fold that in. So there's variable noise, but the noise may be not white. Is that included? I couldn't figure out how this was all, so I'm sure it is.
Yeah.
But do you actually build it in with, let's say, priors on the structure of that, or do you just say, try and do this separation of components that you toss out noise?
So the interesting thing about the domain when you have enough data is that you don't have to think about all of them, because once you have a large enough data, your data set has many realizations of the noise. So the distribution of noise is kind of implicitly encoded in your data itself. your model is just creating some nonlinear mapping between all these realizations of the noise from the data and the signal to the output. So you're essentially in that way marginalizing your work.
Yeah, but you could imagine taking the mini ensemble that you're doing as a training set and rank ordering it according to the relative noise level.
Yeah.
And then if you go down that trajectory to the higher and higher noise, higher and higher noise, you could probably improve things because of that rank ordered tab. You may not be able to, but
No,
that's
you're
just
totally
a
right.
general issue.
And people do that. There's a class of methods which people call self-supervised learning, which are designed to essentially work in the very low data regime, where just adding noise artificially to the data itself, you're increasing the training data by them. And yeah, so people do use that. Just in the regime I showed in my experiments, just because I had like 500,000 spectra, I didn't have to do that, but people definitely are using it. For example, people in my old group, they're trying to do this whole thing, but with space-based imaging. But with space-based imaging, like Hubble and James Webb data, where you have very few label data set. So in that case, they create new data by adding noise and just increasing the volume of the data by different noise.
Yeah, I mean, actually, there are many dimensions to the question I had, but one of them is explicitly what you're just referring to, I think, which is that you have a whole bunch of different observational campaigns, let's say Sloan and Daisy and TPS and all of that. Traditionally, there's always been this huge problem of them not being well calibrated to each other. And presumably, much better calibration can come out of this class of studies. That is to say, you can effectively use these methodologies, maybe not, but you can probably use these methodologies to try and regularize between the different experiments. You know, one of the classic problems we have, I mean, not that it's related to this, is why are the supernova results looking so different depending upon who looks at it, and therefore it makes one think that it's not reliable. But you should be able to put them on the same observational framework without doing re-observing, just using the intrinsic properties of each of the data sets and how they're obtained. I don't know if that's a development in this subject, but it seems like a good path to be on because the theoretical problems are quite interesting.
Yeah, definitely. And people are, not me personally, but I know many people are actually working on this, fusing multiple different observations together.
This sounds like a great opportunity to move upstairs. Thank you, Thank you everyone for joining online. And so we can keep it with work here, so there's plenty more time for
I'll go